Hello and welcome back. This is just a quick recording on the murphree efficiency. So let's head over to the whiteboard. So whereas in the past, when you've drawn and done the McCabe-Thiele analysis, so here's your XY plot. As such, and you've obviously got the equilibrium curve, so something like this maybe. Apologies for any terrible drawing. So you got something like this maybe. Let's just say this was the value of xb here. And up here is the value of xd. See, you have, let's take this point to be ZF. So you have your Q line, you have your SO, and maybe something like this. I'll tell you what, I'll use a straight line. So here's your Q line, and here's your SO. This. You have your stripping line, maybe something like this. Then you've just done your normal step down method. Started here, gone doom, 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 doom. Keep going down, 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 down until you reach there. Then you've just counted the numbers. Steps that took 1, 2, 3, 4. Obviously the we need one more as well, 5, because we need to reach this XB. So 5. Last one's a reboiler, so 4 plates here. Standard stuff that you've done. What the Murphree equation or the Murphree efficiency is saying is that in reality you never reach a bit of an inaccuracy in my drawing. They should reach the. What's saying is you never, in reality, due to inefficiencies of the plate, etc., fluid flow, pressure drops, etc., you never actually reach this equilibrium value y star. And in fact, it's found that you reach a value that's in between y star and this step down line. So step down line is, let's call this one yn minus 1. So the actual vapor phase fraction leaving a given plate is in between these two values. Yeah, so the actual vapor phase leaving would be in this range, somewhere here. And if you take a look at the Murphree efficiency, one thing to note as well, there's one, the Murphree efficiency is set up so that there is one efficiency for the whole of the stripping section, and then there's one efficiency for the whole of the enrichment section, respectively. So when you apply the formula, make sure that once you're looking at a plate below the Q line, you apply the stripping section efficiency, and if you're looking at all the plates above, you apply the enrichment section efficiency. So taking a look at the enrichment side efficiency equation, it's, if you rearrange it for, let's call the actual real value here of the vapor phase leaving a given plate as y dash. So looking at the efficiency, Murphree efficiency formula, you see that y dash is equal to murphree efficiency, looking at the stripping section, sorry, looking at the enrichment section, so it's called EE, y star minus n minus 1, so the step down value of the vapor phase plus obviously, this is shown much clearly in this picture as well. Obviously, you can read off. So for this given plate, following typical McCabe-Thiele, it would touch this. The value that it would point out here would be. I'm just going to take this. So when you do the step down, you'd probably have something like this, like that. So this will be the y star, the equilibrium value. You got your step down value, y dash of n minus 1. I just called it y and minus 1, but in this, the notation is a bit different, but okay. So let's go back. Okay. So looking at this equation, for different values of x, it's up to you. You can choose any value of x that you want. Obviously, since you've already done the stepping, it's probably a lot more clearer to do the analysis based on the the given x values of the steps. So let's call this x1. Obviously, you can pick something like here, then read off your step down and the equilibrium value. That's up to you. But as long as you have a few points in order to make the general curve, should be okay. Let's put x2, x3, etc. So what you can do is that for different values of x, just highlighted here. So these are the values of x we're going to pick. X1, x2, x3, etc. You can generate based on the values of x and using the murphree equation, murphree efficiency equation, but swapping out the efficiencies when you go past the Q line. When you go past the Q line and when you're above the Q line, so with respect to what section that you're looking at, you can generate the appropriate values of y dash. So you get y dash of 1, then y dash of 2, y dash of 3. So what you can do with this is the whole concept of the murphree efficiency is it basically states that because of inefficiencies, you never actually reach the equilibrium value. So obviously, when we're doing the stepping down method, we always hit the, as you can see here, we always hit the equilibrium values, right? We always want to hit we're always hitting these the equilibrium curve at the different points. So what the murphree efficiency tries to do is it's going to modify the equilibrium curve so that when we hit the equilibrium curve, when we do a new stepping method and we once again hit the equilibrium lines, it's going to generate a different result. But obviously, we can only modify the equilibrium curve, the actual operating lines itself, the Q line, SO, stripping lines, they're all the same because they're essentially characterizing the same distillation. You're still operating at the same distillation with the same reflux. You got the same target. You got the same bottoms composition. All of that is the same. You're still using the same tower. It's just that you're just modifying the equilibrium curve. So let me just undo these circles. And so if we plot this now, so I'm just gonna remove some of these things. Just to make it a little bit more clearer to see, I think. Otherwise it'd be quite hard. Okay. So when you plot these equations, sorry, when you plot those points, you generate the new murphree equation, the new equilibrium line. Can't get my words out. So obviously you still have the same y is equal to x line here, something like here. And then when you plot these, you'll see that the parabola of the equilibrium line is a lot more shallow this time around, right? So, which makes sense because inefficiencies means that it requires more plates. And when you do your normal stepping down again, so once again, you probably do something like this. Probably needs to go down one more, but obviously not the best drawer in the world. But yeah, even as a rough sketch, obviously, it's quite terrible because it should probably hit. If we again count 1, 2, 3, 4, 5, 6, 7, 8. This time we got 8, right? So referring back to our previous one, we only had 4 plates for the ideal case, but now we have a total of 8. So as I said, the murphree efficiency accounts for the inefficiencies of the plates, and therefore we require a larger number of plates. And if you plug this back into the equation for overall plate efficiency, so eta 0, ideal plates excluding the reboiler, I'm going to say that to be 4, right? And then plates, ideal plates excluding, no, actual number of plates excluding the reboiler 7. So if you were to do that, you would get an overall efficiency of 57%. As a rule of thumb, this overall efficiency should be quite close to 60%, so pretty close here. So yeah, that's it. Essentially, murphree efficiency code for a new equilibrium curve modifying the previous equilibrium curve, but obviously all the other operating lines are exactly the same.